So what we have is 9 bits for the hypothetical floating point number. The first bit is for the sign of the number. The second bit is for the sign of the exponent. The next 3 bits are for the magnitude of the exponent. And the last 4 bits are for the magnitude of the mantissa. So what we want to be able to do is to be able to take this number 11.8 base 10 and write it in this floating point format which follows that convention. In order to be able to do that, the first thing which we have to do is to be able to see that, hey, how can we write 11 in base 2 and how can we write 0.8 in base 2. So 11 in base 10 to base 2 is 1011 base 2. And you can do this as homework because this is video covers this already. 0.8 base 10 will be 0 radix point 11001 and keeps on going base 2. And you can do this also as homework because this is covered in a previous video. So if we want to see 11.8 base 10 written as base 2 number, then it becomes 1011, which is the equivalent of 11, and then radix point, and then we'll have the equivalence of 0.8 in base 10, which is 110012, which we just wrote. So once we have that, what we're going to have is that we have to take this radix point and move it here because we only want one non-zero digit before the radix point. So we 1.011111001 base 2 times 2 to the power 3. The reason we have 2 to the power 3 now is because the radix point was moved to the left by 3 places. And what we're going to do is we're going to do this in 2 stages. We want to first see that how many bits we're going to take of the mantissa. Since there are only 4 bits for the mantissa, we can only use these first 4 bits, 1011 and base 2. So we're going to forget about these because these cannot be represented because we have only 4 bits for the mantissa. Then we have 2 to the power 3. Now 2 to the power 3 needs to be, the 3 part needs to be written in base 2. So the, 3 will be 11 base 2. So this 3 which we have in base 10 can be written as 11 base 2. But again, we're going to make a small change. We're going to say this is this multiplied by 2 to the power 011 base 2. The reason why we're doing 011 rather than 11 base 2 is because we have 3 bits available for the magnitude of the exponent. So let's repeat this. We have 11.8 base 10 is now written as 1.0111 base 2 times 2 to the power 011 base 2. And now what we have to do is we have to assign it to the 9 bits of this hypothetical floating point. And we're going to see how we're going to going about doing that. So here we have the 9 bits. This is for the sign of the number. This is for the sign of the exponent. These 3 are for the magnitude of the exponent. And these last 4 are for the magnitude of the mantissa. So what we're going to do is we're going to start now filling in these places for the bits with zeros and ones. The sign of the number is positive, so we're going to put 0 here. The sign of the exponent is positive, so we're going to put 0 there. The magnitude of the mantissa is 011, 011. And then we have these 4 bits to be put in the magnitude of the mantissa, 0111. We don't take care of this because this is already assumed, because in order to put a non-zero digit before the radix point, you need a non-zero number, and the only non-zero number which is available in binary format is 1. So we don't need to represent it. It is there, but we don't need to represent it because it will always be 1. So this is the representation of the number 11.8 base 10 in this hypothetical 9-bit floating point representation. Now if somebody said that, hey, if this is the representation, how would you write this number in base 2? You will say, okay, what I'm going to do is I'm going to first say it is plus, because of the fact that the sign of the number is positive. Then I'm going to write 1, then dot, and then what I'm going to do is I'm going to write the 4 digits of the mantissa, 0 1 1 1 base 2 times 2 to the power, and then I'll write the 3 bits of the magnitude of the exponent, 0 1 1 base 2, and then I have the sign of the exponent, which is positively plus. So go ahead and see that what this is equivalent to in base 10, and you will see that it is not equivalent to 11.8 base 10. So that difference between this number and this number will tell you what the round off error is caused by using this hypothetical 9-bit word for our floating point representation. And that is the end of this segment.